This is Lecture 3, Describing Data. By the end of this lecture, you should be able to identify a variable's level of measurement, calculate and interpret a variable's measures of central tendency and variability, construct a frequency distribution bar graph and histogram, analyze frequency distributions, bar graphs, and histograms to describe a variable's distribution, and be familiar with commonly used Greek symbols in statistics. In the last lecture, I discussed how to measure variables. In this lecture, I'm going to discuss how to use simple statistics to describe the average of a variable and its distribution. Recall that a variable quantifies a specific concept we are studying, such as war or voting behavior. Additionally, all variables have to have a unique name. And all variables take on numeric values and must have at least two values, such as 0 or 1. In the first part of this lecture, I'm going to show you how to classify a variable based on the values the variable can take. You can classify a variable as nominal, ordinal, interval, or ratio level. Remembering the word noir is an easy way to remember these four terms, as the letters in the word noir are the first letters of these four words. N-O-I-R. Noir means black in French. Nominal level variables divide the subjects or observations in your variable into different categories. The categories are exhaustive, meaning that you included all possible categories. The categories are also mutually exclusive, meaning that you can only place a subject or observation in your dataset into one of the categories. And note, while there is a numerical difference in the categories, there is no inherent order in the data. One category is not greater than another. For example, if you were collecting data on voters' party identification, you would have three different categories in your data: Republican, Democrat, and Independent. These categories are mostly exhaustive, as they capture the main three party identifications in the United States. These categories are also mutually exclusive, because a voter cannot be classified into categories such as a Republican and a Democrat. And even though these categories have different numerical values, there is no inherent order in the variable. Even though independents are given a 2, they are not greater than Democrats, a 1, or Republicans, a 0. In other words, the numbers do not demonstrate differences in quantity. They are just arbitrary labels we assign to the categories to demonstrate that there are different categories. Ordinal level variables also divide the subjects or observation in your variable into different categories, such as not support or support for a candidate. The categories are exhaustive, meaning that you included all possible categories. The categories are also mutually exclusive, meaning that you can only place a subject or observation in your dataset into one of the categories. In addition, there is inherent order with an ordinal level variable. The categories have inherent order. But note, the numerical space between the categories is not inherently fixed. For example, many surveys ask respondents about the extent to which they support a candidate. The surveyors divide the support answers into numerical rank order categories, such as giving strongly oppose a -2, oppose a -1, neutral a 0, support a 1, and strongly support a 2. As you can see, the least support has the lowest value, -2, and as a respondent's support increases, the values go up by 1. However, note that while there is an inherent numerical order in this data, the spaces between the categories are not inherently fixed. For example, for one individual, the difference between support and strongly support could be smaller than the difference between strongly oppose and oppose. Interval level variables are ordered. The spaces between the categories are fixed. For example, the spaces between 1 and 2 equal the same distance between 2 and 3, 1 unit. But with interval level variables, there is no true 0. Ideology could be an interval level variable. You could have a continuous ideology variable that ranged from 0, extremely liberal, to 5, moderate, to 10, extremely conservative. But the 0 in this case is an artificial 0. We could have moved the scale from -5 to 5 instead, and 0 would become moderate, and it would not fundamentally change the nature of the variable. Last, ratio level variables are ordered, the spaces between the values are fixed, and ratio level variables have a true 0. For example, military spending is a ratio level variable. It ranges from 0 to any positive value, the spaces between the values are fixed, and it has a true 0. 0 means 0 military spending. Next, I'm going to show you how to use basic statistics to describe data. First, I will discuss measures of central tendency. Central tendency is just another way of saying the average or typical case of a variable. There are 3 measures of central tendency: the mode, median, and mean. The mode is the most common or most repeated value of the variable. In order to find the mode by hand, you arrange the values from the smallest to largest. Then you find the most repeated values in the data set. As a simple example, imagine we had a variable that took on the following values: 7, 2, 10, 5, 6, 7, 7. To find the mode, I would arrange the values from the smallest to largest: 2, 5, 6, 7, 7, 7, 10. Then I would find the most repeated value. The most repeated value is 7. It is repeated 3 times, and no other numbers repeat more than 3 times. So 7 is the mode. To demonstrate how to calculate the mode for a more realistic variable, I will use the common space scores from the 106th Congress. Common space scores measure House members' ideological positions by using roll call votes. Common space scores range from -1 to 1, with values less than 0 being liberal and values greater than 0 being conservative. In this particular example, I arranged the data from the smallest to largest value. There are 2 modes in this data. There is a mode for Democrats, -0.374, and a mode for Republicans, 0.359. In both cases, there are 6 observations with the value of -0.374, 1, 2, 3, 4, 5, 6, and 0.359, 1, 2, 3, 4, 5, 6. There are no values in the data set where 7 or more observations share the same value. The second measure of central tendency is the median. The median is the middlemost value of a variable. It cuts the variable in half with the lowest 50% of values on one side and the highest 50% of values on the upper side. To find the median by hand, you arrange your variable from the smallest to largest value. Then you find the median observation number. The position of the median when you have an odd number of observations is equal to the number of observations plus 1 and that value divided by 2. The median observations value is the median. Going back to our simple example, imagine we tried to find the median for the variable that took on the following values: 7, 2, 10, 5, 6, 7, 7. I would start by arranging the values from the smallest to largest. Then I could count the number of observations: 1, 2, 3, 4, 5, 6, 7. There are 7 observations. The position of the median is n plus 1, and that value divided by 2. Recall that n is just the number of observations. So the position of the median is 7 plus 1, which is 8, and that number divided by 2, so 8 divided by 2, which is 4. So observation 4 is the median, 1, 2, 3, 4, and its value is 7, so 7 is the median value for this variable. Now for a more realistic example, in our common space score example, there were 437 observations. 437 plus 1 is 438. 438 divided by 2 is 219. The median observation number is observation 219. I arranged the data from the smallest to the largest value. Observation 219 has a value of 0.137. So the median is 0.137. If the median house member has a common space score of 0.137, who do you think controlled the House of Representatives? Republicans or Democrats? It was Republicans. Recall that common space scores greater than 0 indicate a House member is conservative. The median tells us in this case that the average House member is conservative, indicating that Republicans control the House of Representatives. I showed you how to find the median for a variable with an odd number of observations. Now I'm going to show you how to find the median for a variable with an even number of observations. With an even number, the calculation for the position of the median will produce a number that will have a 0.5 as a decimal at the end. The median is the average of the values for observations below and above the position of the median number. Let's say we have a common space variable with 436 observations. We should run the same calculation as before. The position of the median is equal to the number of observations plus 1, and that value divided by 2. If we have 436 observations, our calculation would produce 218.5. So we get a number with 0.5 at the end. So what we do is take the observations that are below this value and above this value and find the average value of those observations. So we would calculate the average of observations 218 and 219. Observation 218 had a value of 0.135. Observation 219 had a value of 0.137. The average of 0.135 and 1.37 is the sum of these two numbers divided by 2, or 0.136. The third measure of central tendency is the mean. The mean is the sum of a set of values divided by the total number of observations. Formally, the equation looks like this. X bar means the mean of X. Any variable with a bar over it indicates that it is the mean of that variable. The Greek letter sigma, capitalized, means the sum of. In this case, it means the sum of all the observations in X. And n means the number of observations. Going back to our simple example, imagine we wanted to calculate the mean of the variable that took on the values 7, 2, 10, 5, 6, 7, 7. To find the numerator, sigma x, we would start by adding the values together. 7 plus 2 plus 10 plus 5 plus 6 plus 7 plus 7 equals 44. Then for the denominator, we would just find out how many observations there are. 1, 2, 3, 4, 5, 6, 7. There are 7 observations. So 44 divided by 7 is 6.3. The mean is 6.3. For a more realistic example, going back to the common space scores variable, the mean of the common space scores are the sum of the common space scores divided by the total number of observations. I calculated this by hand. The sum of the common space scores was 21.788. The total number of observations was 437. 21.788 divided by 437 equals 0.05. The mean of the common space scores was 0.05. So, in sum, there are 3 different measures of central tendency, the mode, median, and mean, and all 3 measures give us different values, as in the common space score example, leading us to draw different conclusions about the average or typical case of a variable. So when do we use these 3 different measures? If we are examining a nominal level variable, we should only use the mode. Recall that the values of a nominal level variable have no order. The mode does not assume a variable has order, but the median and mean do assume a variable has order. Hence, with a nominal level variable, we should only use the mode to describe the typical case of a variable. With an ordinal level variable, the values of the variable have order, but the spaces between the values are not fixed. We can use the mode for an ordinal level variable, because the mode simply tells us the most common value in the data. We can also use the median because we can order the data from smallest to largest and find the middlemost value. We can also use the mean, but it is debatable whether it makes sense to use the mean for an ordinal level variable. The mean assumes that the spaces between the values of a variable are fixed, which is not always the case with ordinal level variables. Nevertheless, social scientists often use the mean to describe an ordinal level variable. Next, recall that interval and ratio level variables are ordered and continuous. Hence, we can use their mean, median, or mode to describe the typical value of these types of variables. Back to the common space score example, recall that the common space scores are ordered and continuous, but they don't have a true zero, so common space scores are interval level. Hence, we could use mode, median, or mean to describe the variable. However, the mode, median, and mean tell us different things about the typical value of this variable. According to the modes, the typical members of the house are either liberal, with a score of negative 0.374, or conservative, with a score of 0.359. According to the median, the typical member is moderately conservative, with a score of 0.137, and according to the mean, the typical member is moderate, with a value of 0.05. So which one is correct? Since the median and mean are greater than 0, the average member is likely conservative, but based on the mode, it is likely that there is a significant liberal presence in Congress as well. To make a more informed judgment, we would need to determine how the data are distributed in a histogram to find out, which is a topic of Lecture 3, Part 2, next week. In this part of the lecture, I'm going to show you how to calculate the variance and standard deviation for interval and ratio level variables. The typical or average case of a variable is not the only statistic that we can use to describe a variable. How a variable's individual observations deviate from its mean also matters. Imagine you are examining the following two variables. Both of these variables have the same mean, 100, but for each variable, observations deviate from the mean of 100 differently. In the first case, observations take on values very close to 100, 90, 95, 100, 105, 110. The observations are clustered around the mean. In the second case, observations take on values very far from the mean, negative 100, 0, 100, 200, 300. The observations are dispersed. So it is important to not only use the mean to describe interval and ratio level variables, it's also important to know how observations are distributed. The variance and standard deviation tell us how often observations deviate from their means. To calculate the variance, s squared, we subtract the mean of the variable from each individual observations, square that, add the values together, and divide by the total number of observations minus 1. To find the standard deviation s, we simply take the square root of the variance s squared. To illustrate how to calculate a variable's variance and standard deviation, I will use a variable that measures the number of parties in a country. Imagine the variable took on the following values: 333, 22, 42, 634. The first step is to calculate the mean of the variable. Recall that to calculate the mean, we add all of these values together and divide by the total number of observations. The mean number of parties was 3.2. Then we subtract the mean from each observation. 3 minus 3.2 is negative 0.2. 3 minus 3.2 is negative 0.2, and so on. What this is doing is showing us by how much observations are deviating from the mean. Then we square these values. Negative 0.2 squared is 0.04. Negative 0.2 squared is 0.04, and so on. One intuitive reason for squaring these values is that it gets rid of the negative values, because we don't care if observations deviate in a positive or negative direction from the mean. We just care that they deviate. Then we add all the squared deviations together. 0.04 plus 0.04 plus 0.04 plus 1.44 plus 1.44 plus 0.64 plus 1.44 plus 7.84 plus 0.04 plus 0.64 is 13.6. 13.6 is our numerator. Then to find the denominator, we find the number of observations and subtract 1 from it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 observations, so 10 minus 1 is 9. Now we divide. 13.6 divided by 9 is 1.5. So our variance, s squared, is 1.5. Note that this calculation is similar to calculating a mean. You add all the squared deviations together and divide by the total of number of observations minus 1. Here we are trying to find the average squared deviation. Note that we minus 1 in the denominator because we are working with a sample, something that we will discuss later in the course. We take the square root of the variance to find the standard deviation. The standard deviation, s, is the square root of 1.5, which is 1.2. To interpret the standard deviation, we would first state our mean, then we would say observations deviated about standard deviation units from the mean on average. The units just tell us what units the variable is measured in, such as dollars or people. So going back to our example, we would interpret the mean and standard deviation as follows. On average, there are 3.2 political parties in a country. Observations deviate about 1.2 parties from the mean on average.